We divided stream ciphers into two classes, synchronous stream ciphers and asynchronous stream ciphers, which is also called self-synchronizing stream ciphers. So, as these names suggest, you can guess that synchronization is somewhat important in the topic of stream ciphers. So, let's see these two different classes of stream ciphers and see how the synchronization is important. The types of stream ciphers we have considered so far belong to the class of synchronous stream ciphers because they didn't use the stream cipher bits or bytes in their next state function or the encryption function. To use the ciphers, the sender and the receiver must be synchronized. This means that they should be able to produce the same key stream so that they can perform the same encryption and decryption. So for this reason, they must set the state at the same position. So their internal state should be the same at the same time, but also they must use the same key, of course. If the synchronization is lost, then the decryption fails. So at any time t, if receiver or the sender person has a different internal state than the other one, then the synchronization is lost. So synchronization can be lost due to many factors. Sometimes device failures, so these are hardware problems. Sometimes there are problems in the communication channel. This can be related to your position, actually. For instance, if you're inside a building which has a lot of metal in it, like if you're in an elevator or so on, the Wi-Fi or your GSM communication might not be good. But also if you're, at the one side of a mountain and the antennas are not directed to that way, direction, then you may not have enough reception. But also there might, of course, there might be a jammer around, so they might be blocking the communication channel. These jammers can also work in the following ways. There might be an active adversary inserting ciphertext digits to your communication or deleting your ciphertext digits. So this will cause a synchronization loss. So this is actually happens in Wi-Fi or GSM communication. So at some point you stop hearing the person you are talking to, or on the other hand, you hear them, but they don't hear you. So you have to resynchronize in these situations, but most of the time, if it is not a self-synchronizing algorithm, the best thing you can do is to reset the communication. So if it is a GSM communication, cancel the communication and recall the person. Or if it is Wi-Fi, for instance, if you get distant from the router and come back, most probably you will have some connection problems. So just turn off the Wi-Fi and then turn it on again, and it will work, which is a common thing in computer science. So to restore the decryption, additional measures have to be employed. Reinitialization, this is actually, what I actually mentioned, turning it off and on again. Or you can place special markers at regular intervals. So if you do it, this would be good, because even if the connection is lost, since if you receive the same, if you observe the same special marker, then after that point on, the synchronization will be obtained. You can also try all possible key streams if the synchronization is lost due to 1 or 2 bits of insertion or deletion. But of course, in practice, nobody would, use that technique, as far as I can guess. So an active adversary also might cause a synchronization loss. So let's look at what can an active adversary do. A modification of a ciphertext digit does not affect the decryption of the other digits, so no error propagation. Since we are simply XORing in the key stream with the plain text, then if the active adversary flips 1 bit, it doesn't affect the other bits. As a result, an active adversary who deletes or inserts ciphertext digits can be detected by the decryptor. So this is important, because if somebody inserts or deletes a ciphertext digit, the synchronization is lost. So you can detect there is something wrong with the communication. So if it is not due to a hardware failure or a communication channel failure, you might think that there's an active adversary. On the other hand, an active adversary may change the selected ciphertext digits, knowing the exact results of those changes on the plaintext. So if somebody already knows the effect that is going to be observed by modifying the ciphertext digits, they might cause some problem by modifying the ciphertext digits. So some additional mechanisms must be employed in order to provide data origin authentication and data integrity guarantees. So this is why we will talk about message authentication codes and also authenticated encryption. Let's move on to asynchronous stream ciphers, which are also known as self-synchronizing algorithms. When the key stream is generated as a function of the key and a fixed number of ciphertext digits, we obtain a self-synchronizing stream cipher. So the next state function actually also uses the, for instance, last t digits of the ciphertext. So this is actually enough, because even if somebody deletes, inserts, or modifies your ciphertext so that you lost your synchronization, after some point on, if there are no more active attacks, the person will receive same amount of here, like the k ciphertext digits in a correct order. So once they receive that, their internal state will be the same. So at that point on, the following ciphertext digits they receive would be correctly decrypted. So this is why asynchronous stream ciphers actually can provide self-synchronization. Since the encryption function depends on k fixed ciphertext digits, synchronization is possible if ciphertext digits are deleted or inserted. The cost of resynchronization is a loss of a fixed number of plaintext digits. When a ciphertext digit is changed, inserted, or deleted, the decryption of at most k ciphertext digits may be incorrect, so there is a limited error propagation. But still, some additional measure must be employed in order to provide authentication and data integrity guarantees. So since in these ciphers we have resynchronization, so even if there is an active adversary, you might not detect it, because after some point on you will always have the resynchronization. So you might think that the previous problem might be due to a communication loss or something. So let's compare asynchronous versus synchronous stream ciphers. Each plaintext digit has an effect on all the remaining ciphertext digits in an asynchronous stream cipher. This implies that the ciphertext does not inherit the statistical properties of the plaintext. As a consequence, asynchronous stream ciphers may be more resistant against attacks based on plaintext redundancy. Due to self-synchronization and limited error propagation properties, the detection of an active adversary is more difficult than for synchronous ciphers. The input of the generator uses the ciphertext. Thus, the adversary has a partial knowledge about the variables being used. So this is important, because since we already assumed that the communication channel is insecure, the attacker already captured the ciphertext digits. So k ciphertext digits also determines the internal state, so part of the internal state. So but of course the attacker doesn't know the key, but still they have some partial knowledge about the variables being used. As the key stream depends on the message, these generators have a limited analyzability. So this is one of the problems. It is hard to check the security of this kind of designs, because the security depends actually on the message you are encrypting, because the internal state depends on the ciphertext digits. So for this reason, in crypto community, there isn't any automatic or good way to analyze this kind of ciphers.